Today we are starting with section 11.1, sequences. So up till now we have studied functions whose input values represent real numbers. An example of that is an input variable x can not only take on the value 3, but values arbitrarily close to 3. What this means is if we wanted to look at a table of values, and here I'm going to put a very simple function of just f of x is equal to x. So what that means is we can look at 2.9, 2.99, and 2.999 and see what those function values are going to be. And obviously in this case these values are approaching 3 as well. So this property, this is what makes us able to use things like limits, continuity, and differentiation. Because to think about those, continuity, differentiation, and integration are built off of limits. But what happens if we remove this property? This is where sequences comes into play. So if we remove this idea of being able to become arbitrarily close to a single value, meaning that we can't do steps like 0.9, 0.99, and so forth, then we get a sequence. So a sequence is a function. It is a function whose domain is restricted. And here it's restricted to values on a discrete set. Okay, so typically this discrete set, and what we are going to be dealing with, is the positive integers. All right. Another way a sequence can be thought of is as a list of numbers, but we're going to be a little bit more specific than just a list. So it's a list of numbers written in a definite order. So that means the first value is going to say the first value and so forth. So we're not going to be mixing this in. So we're going to have A1, this is just an arbitrary example, A1, A2, A3, and so forth. Now typically to represent a sequence, we are going to write a sub n instead of function notation, which we are used to when we talk about a function. And there is a reason for that. So here our function notation could have been f of n, where n is an integer. But in this idea, we are wanting to make the clear distinction of what a real valued function is, like f of x is equal to x squared, versus a sequence. And the reason that we are doing that is because later on there's a theorem that we will be using to talk about convergence and divergence of a sequence that relies on those two notations. So we want to make a clear distinction. Are we dealing with a function that's dealing with real variables and we can have this arbitrary closeness going on? Or are we dealing with a sequence where it has a definite order? So another notational thing that we will see is the sequence A1, A2, A3 is typically denoted as A sub n with parentheses around it, or to be very specific, we can throw some indices on here, just like what you do with the summation. So here it has the indices n is equal to 1 and it goes to infinity. If we were dealing with a finite set, you could see it as n goes from 1 to 5. And that's just to indicate, are we dealing with an infinite sequence or are we dealing with a finite sequence? All right. To get us used to this notation, we're going to first write the 4 values of the beginning of this sequence. N plus 1 over 3 to n. So this a sub n, this is what this value is. So a sub n is equal to this formula here. And we'll later see that this is really nice to have a formula to go off of because that makes it an easier way to evaluate if a sequence is going to to converge or diverge. Okay, so plugging in our values, we're going to look at a sub 1. So this is going to be our first value. So just plugging in n is equal to 1 into our formula. So we're going to get 2/3 out of this. Then when I plug in 2, I'm going to get 3/6, or we can reduce that down to 1/2. A sub 3 is equal to 4/9, and a sub 4 is equal to 5/12. Okay, and that's the first 4 values of the sequence. So if we were to write it out in set notation, we'd have 2/3, 1/2, 4/9, 5/12, and so on. And that's what it would look like. All right. Sometimes we will be given a sequence and we need to find out what this formula is. So this is a good example here. So find the formula for the general value a sub n of the sequence. So in this case, let's look at the pieces separately. So we're going to look at a couple different situations when approaching these. So if we look at just the numerator, disregard the negative for now. We're going to actually bring that negative in at the very end of this example. So if we look at the values, we have 3, 4, 5, 6, 7, and so forth. So we can clearly see that the next value should be 8, then 9, and so forth. All right. So the numerator, we want to start with 3. And we want to increase it by 1 every single time. Well, we need to start with when n is equal to 1. So the nth value should be, so again, the numerator is what we're focusing on. The nth value for this should be n plus 2. Now let's see if that makes sense. Well, when we look at a sub 1, if we're just looking at the top, we plug in 1 here, we get 3. A sub 2 would be 4. A sub 3 would be 5, and so forth. So we get exactly what we need. So we know the numerator has to be n plus 2. All right, so now let's look at the denominator. Okay, so the denominator here, let's look at what's going on. So we have 5, 25, 125, and so forth. Well, if we thought of addition, we'd add by 20 for the first one, but then we'd have to add by 100 and so forth to get to the next values. So that's not a really good way to set up a formula for this, because we'd have to be changing that incremental value as we do this. Another way that we could look at it is, well, let's look at, see if there's a commonality between these. Well, 5 to 25, well, that's the square. And then 125, well, that's 5 cubed. And 625 is 5 to the 4th. So here, these are just powers of 5 that are increasing. So we can write the denominator as 5 to the n. And let's see if that makes sense. So if we were looking at A1, we would have here 5 to the 1st, which is 5. And then A2, which is 5 squared, which is 25. And so we can clearly see that this is going to create the denominator. All right. So now we have our setup. A sub n is equal to, and I'm going to leave some space here, you'll see why here in a second, of n plus 2 divided by 5 to the n. I'm going to fix that 2 real quick here. All right, so now we have to deal with this negative sign that's going to be alternating between each of these values. So notice we start with a positive, then negative, positive, so forth. Okay, well, a way that we can deal with that is throwing in a -1, but we've got to be careful about this. Okay, I could say, well, hey, it's -1 to the n. But then that would mean if I plug in 1, I should have a negative value out front. Here I need a positive. So I'm going to erase this real quick. So a way to deal with that is we still have this -1, but we want to make sure that we have a positive value. So there are a couple ways that we could deal with this. So we could have n minus 1, and so let's check that. Well, when n is equal to 1, we're going to get to the 0 power, and therefore this would be positive 1. And then when we plug in 2, we're going to get to the first power, so that would be -1. And so notice that this is going to match our sequence with here. So this is our formula for the general value of a sub n of the sequence. Okay, so we can even write this, that this is equal to -1 to the n minus 1 times n plus 2 over 5 to the n. And that would be our sequence. And if we wanted to be really specific, we could say n is equal to 1 to infinity. Okay? All right, moving on. Assuming that the sequence continues, find the formula for the following. -3, 2, -4 thirds, 8 ninths, -16 27ths, and so on. So with this one, it's a little bit harder at the very beginning to determine what's going on with it. We do have an alternating sign that is occurring. So we need to make sure that there is going to be a negative sign that is going to come out. So we can go ahead and use the very beginning of that and say, okay, well, we know we're going to have -1 to the n as a starting point. Okay, so that's one way to start. The next thing is, well, what are we doing? You know, it's kind of hard to see, well, I add 5, but then adding 5 is not going to get me from 2 to -4 thirds. Okay, so there's got to be something else that's in play. So looking at a little bit further down the line, we can see, hey, this is 4 going to 8. Well, that's either adding 4 or multiplying by 2. And then 8 to 16, well, that's multiplying by 2 again. So it stands to reason here that we are multiplying at least by 2 on the top, and then looking at the bottom, we have 3, 9, then 27. Well, these are just powers of 3. So let's check that. Well, if I multiply negative 3 by 2 over 3, that would give us 2. Okay, so we know we're going to have 2/3 as our multiplier. Okay, but we got to be careful. We can have 2/3 here, but we need to make sure that we get negative 3 out of this. So we have to be very, very careful. So a way that we can do this is, well, we can say, well, this is negative 3, and then we multiply by 2/3. So we want a 0 to go in this place. So a 0 power. But I still need that negative 3 to pop up. Well, I'm going to have a negative, so I can have a 3 here. So this looks like a jumbled mess, and that's okay. We can actually deal with this here in just a second. So if I bring in that negative to the 3, that would essentially reduce this down by 1 power. So that would be negative 1 to the n minus 1, and then 2/3 to the n minus 1. Notice that they have the same powers, which allows me to rewrite this a little bit more truncated form of negative 2/3 to the n minus 1. So let's check that. If I plug in 1, I'm going to get 0 out, so this is going to give me positive 1 within here, and then I'm going to have negative 3, which is the first term that we need. Okay, let's check it for the second term, because we can't just check the first and say we're done. So I plug in 2. Well, this is going to be negative 1 to the, or negative 2/3 to the first power, times negative 3. Well, the negatives are going to cancel. The 3's are going to cancel, leaving me a positive 2. And just for one more check, just to see, because we have the time, if I plug in 3, I'm going to get squared here. So this is going to be 4/9 multiplied by negative 3, and the 3's are going to cancel, giving me 4/3, and that negative is still going to be there. So this works out for us. Okay? All right. So take a second and pause the video if you need to, and look at the next sequence. I want you to find the formula for the sequence 5, 8, 11, 14, 17, and so on. All right, so if you're coming back to us now, we're going to look at this. Note that here, the differences are adding 3, and so forth. And that's a constant reminder. So if we look at this, we know A1 is going to be 5. A2 is going to be, well, that's 5 plus 3. A3 is equal to 5 plus 3 plus 3. Or another way to write that is equal to 5 plus 3 times 2. A4 is going to be 5 plus 3 times 3. All right, so, well, that means if we were to continue this pattern on, this would be 3 times 0. This would be 3 times 1. So how could we generate these values using n? Well, a sub n is going to be 5 plus some multiple of 3. So we know that. All right. Well, I need to get 0 out as the first one. Well, the only really way to do that is have n minus 1. All right, so let's check that. Well, if I plug in 2, I'm going to get n minus 2 minus 1, which is 1. And so I'm going to get 5 plus 3, which is equal to 8. And then when I plug in 3, I'm going to get 2 here, so that matches this pattern. When I plug in 4, I'm going to get 3 here. So a way to write this is now 5 plus 3n minus 3, and then we reduce this down to 3n plus 2. and that's our formula for this sequence. So this is to show you different ways of looking at sequences. So we can have addition going on, we can have a multiplication using just powers, and we can also be multiplying by some common ratio that's occurring. And that idea of a common ratio is the background behind geometric sequences and geometric series when we get into series here in the next section. Okay? Well, this is great if we can come up with a formula. But some sequences do not have a simple defining equation. So here's a couple examples of what that means. So let a sub n be the digit in the nth decimal place of pi. So just to remind ourselves what pi is, and so forth. So 3.14159 and change. All right, and a lot of change. So here, what this would mean is that we would have the sequence 1, 4, 1, 5, 9, etc. Well, there's a problem with this. It is well defined. We know exactly how it's written. It's in a definite order. We do with each next decimal point that we're looking at. But we don't have a formula for this. Because if we had a formula for this, we'd know exactly what the value of pi is. Okay? So this is an example of one of those that we do not have some clear defined equation to go with this. Another more famous one that we can deal with is the Fibonacci sequence, and I believe that everybody in the world has at some point heard of the Fibonacci sequence. And this is what we call a recursively defined sequence, and we actually use f sub n in this situation because it's dealing with Fibonacci. It's a named sequence for this case. So how it's written is we first define the first couple of values. F of 1 is equal to 1, and f of 2 is equal to 1. From that point on, it's recursively defined by the following. F sub n is equal to f sub n minus 1 plus f sub n minus 2, where n is greater than or equal to the value 3. So if we were to look at this sequence, it'd be 1, 1, and then we add the two preceding values before this. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, then 8, then 13, and so forth. So here, again, the sequence does not have a clear defined equation to go with it. It does have a recursively defined formula, but that's a different thing. All right, so now we're talking about convergence and divergence, which I kind of illustrated at the very beginning, and now we're actually going to talk about what this means. So to give us an idea of what's going on, let's consider the following sequence. 1/2, 2/3, 3/4, 4/5, and so on. So its formula is n over n plus 1. Well, if we looked at these, this looks like it's approaching a particular value, doesn't it? It looks like it's going to be approaching 1. It's never going to get there because the denominator is one value greater than the numerator. But think about that idea. That's a limit idea. Like we arbitrarily get close to a value. Here we're arbitrarily getting close to a value of 1. All right? So this gives us the idea of what convergence is. So a sequence a sub n has a limit, we'll call it L, and we write that limit as the limit as n approaches infinity of a sub n is equal to L, or another way to state this, as the values of a sub n approach L, or another way to state that, as a sub n approaches L, as n approaches infinity. All right? So if we can make the values, this was what this means. Okay, and this is just going to the basic idea of what a limit is. If we can make these values of a sub n, write that a little bit bigger, as close to L as we like, by taking n to be sufficiently large. So n to be sufficiently large. All right. So what that means is as we look further down the sequence, I'm not talking about not just the first couple of terms. We're talking about going out towards infinity. As we make n larger and larger and larger, what are we approaching? Are we approaching a particular value? What's going on? So that means if this limit exists, if we approach a particular value, we say that the sequence converges or is convergent. And likewise, if the sequence blows up to infinity or has oscillating behavior, then we're going to say that the sequence diverges or is divergent. So one way to think about convergence of a sequence is looking at the tail end of the values or approaching some number L. Okay, and to help illustrate this idea, or to kind of connect it with what we have seen before, the only difference between the limit of a sequence and the limit of a function, and here when I mean function, I'm talking about like f of x, is that n is required to be an integer, and more specifically a positive integer. Okay? Which leads us into our theorem. If the limit as x approaches infinity, so notice now we're talking about f of x now, is equal to L, and f sub n is equal to a sub n, meaning for every single integer we are generating the values of the sequence for this particular function, where n is an integer, then we can say the limit as n approaches infinity, so notice now we're talking about the sequence, of a sub n is equal to L as well. So what this means graphically is, say we have a particular function, all right, and this function is generating at these integer values the sequence. We're matching these guys up or pairing them together. So notice, another way to do this is connecting the dots, is that we're using the function and the ability to talk about arbitrarily closeness using the true definition of what a limit is. We're able to say that the limit of the sequence is also approaching value. And notice here, what we're really talking about is, if we were looking at a function, we're talking about the horizontal asymptote. Is it going to a particular value as it approaches infinity? And so that's what it means for a sequence to converge, is if further down the line we're seeing this convergence to a particular value. All right. So some things that we have seen before from previous lectures is we know that the limit as x approaches infinity of 1 over x to the r is equal to 0 when r is greater than 0. What this means is as long as we have a positive power of r, as x approaches infinity, the denominator is going to blow up to infinity, therefore the whole fraction is going to go to 0. If this is the case, then the sequence (1 over n to the r), where r is greater than 0, converges by our theorem. And then we can say the limit as n approaches infinity of 1 over n to the r is equal to 0 if r is greater than 0. All right? So we use the function to talk about the sequence converging. Okay, so if a sub n becomes large as n becomes large, we'll use the notation just like what we have before, that the limit as n approaches infinity of a sub n is equal to infinity. So this means that the sequence is going to diverge to infinity. Okay, just like our definitions before about limits, we're not saying that the limit is equal to infinity, we're saying that it goes off to infinity. So this is just our typical notation that we have seen before. So the nice thing is if we do have a convergent series, a convergent sequence, then the limit laws hold for the sequences as well. Meaning we get to use all of the properties of limits if we have a convergent sequence. Meaning we get to use the sum difference rule, constant multiples, product, quotient, and power rules. Not only that, we can apply things like the Squeeze Theorem. So for us, we're going to adopt it for sequences, meaning if we have three sequences, a sub n, which is less than or equal to b sub n, which is less than or equal to c sub n, for all n greater than or equal to n sub 0. So at some point, what this means is it could be for the whole sequence, or after a certain point, we see that we have this order that a sub n is less than or equal to b sub n, which is less than or equal to c sub n, and the limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity of c sub n, which approaches value L, then the limit as n approaches infinity of b sub n is also equal to L. So this is just a rehashing of the Squeeze Theorem now applied to sequences. And we also get a really nice theorem coming from absolute values. This one is a little bit more interesting to use, and it's a one-way street for this one. So if the limit as n approaches infinity of the absolute value of a sub n is equal to 0, then the limit as n approaches infinity of a sub n is also equal to 0. So this is going to come in handy, especially if we have something that is alternating in sign. And so if we had like a dampened sine or cosine wave, we can use that to our advantage because sine and cosine take on both positive and negative values. Now we'd have to have a dampening, meaning it's reducing down to a certain value. So to start things off, we're going to look at several of these examples. I know I flew through these theorems, but we are going to apply them here in just a second. So I want to find the limit of n over n plus 1, this sequence. Okay. The nice thing here is I can look at this directly. So as n approaches infinity, we have n over n plus 1. So based upon this, I want to first illustrate we cannot apply L'Hopital's rule to this one, and there's going to be another one that we're going to look at here in just a second. And it's because we're dealing with functions that are based upon integers, not real numbers. But there are still those algebraic ideas that we can use. And remember back in Calc 1, we divide by the largest power of n and the denominator all the way through. So if we do that, we're going to get 1 over 1 plus 1 over n. Well, as n approaches infinity, this is going to blow up to infinity as well, but then the whole fraction here of 1 over n is going to go to 0, which leaves us with 1 over 1, or 1. And so as n approaches infinity, we're going to say that this is convergent, or converges. All right. So the next one we're going to look at. Take a second and determine if the sequences converge or diverge. Here a sub n is equal to 3 plus negative 1 to the n, and b sub n is equal to n over 1 minus 2 to the n. So pause the video for a second and take your time, work them out, and then we'll check ourselves. All right, so let's look at these values. What's going on here? Well, a sub 1 is going to equal, well, 3 plus negative 1, so that's going to give us 2. A sub 2, well, all that's going to do is change the power of n here to 2, meaning that we're going to get positive 4 out of this. And then a sub 3 is equal to 2, a sub 4 is equal to 4. Notice that with every even value of n, we're going to get 4 out, and every odd value, we're going to get 2. So this is oscillating between 2 and 4. So this is divergent. And I'm going to give the reason here so that way when you look back at this, is it diverges because of oscillating behavior. All right, so now with the next one. B sub n is equal to n over n minus 2. So this one we can apply our limit as n approaches infinity of n over 1 minus 2 to the, or 2n. So here this is the same principle of what we applied before. I'm going to divide all the way through by the largest power of n in the denominator. So I'm going to get 1 over n minus 2. And therefore we're going to get negative 1/2. So this converges. Right? And it's that simple. So the next one. Show that n squared over 2 to the n minus 1 converges. All right. So this one's a little bit more tricky, especially since I have an exponential function and then also a power function built in here. So we would like to go ahead and say, hey, I could just apply L'Hopital's rule to this, right? Well, that would be great, except L'Hopital's rule does not apply in this particular situation. So I'm going to make a note of that up the top here. All right, so pay attention to this one. We cannot apply L'Hopital's rule to sequences. All right. Or you're like, well, then what do we do? Because we need to be able to see if this is convergent or divergent. This is where our theorem is coming into play. If we can find a function that behaves exactly like the sequence for all integer values, then we can apply L'Hopital's rule to that one. Well, it's almost kind of like cheating, and it feels that way, but a function that we can use is, consider f of x is equal to x squared over 2 to the x minus 1. Now let's look at the limit. As x approaches infinity of x squared over 2 to the x minus 1. All right, let's double check to make sure that we can apply L'Hopital's rule. It's not immediate, so we are going to validate this. Well, as x approaches infinity, the exponential here on the denominator is going to go to infinity, and so is the numerator. So I can apply L'Hopital's rule right off the bat. And now we're going to get 2x divided by 2 to the x natural log of 2. All right, so let's look at this. Well, we can't really simplify anything, but we can look to see what happens as x approaches infinity. Well, as x approaches infinity, the numerator is still approaching infinity, and so is the denominator. So it means we get to apply L'Hopital's rule one more time. Hopefully it's one more time. We have seen that before. So the numerator, we're going to get 2. And on the denominator, we are going to get 2 to the x. Natural log of 2 times the natural log of 2. So I'm just going to square that. Well, notice here, as x approaches infinity, we have 2, so it's static. And then the denominator is blown up to infinity, so we're going to get 0 out. Well, this means, by our theorem, the limit as n approaches infinity of n squared over 2 to the n minus 1 is also equal to 0. Therefore, this converges. That's exactly what that means. Okay, so notice here, do not immediately apply L'Hopital's rule to sequences. I'm just warning ahead of time. If I see it on one of our take-home tests, then you're going to get points taken off immediately. So you need to show that you're switching it to a function first, applying L'Hopital's rule, then making a connection with the theorem. All right. So the next one. Let's look at the evaluating the limit as n approaches infinity of negative 1 to the n over n, if it exists. So if we looked at this, we would notice I'm just going to be alternating in values, and so this would be oscillating behavior. But there's a way to check first. Remember our theorem about absolute values. Okay. Let's look at the absolute value of this particular sequence. All right. Well, if we have that negative 1 to the n over n, that's going to become just 1 over n. Applying our limit, we can clearly see, hey, this 1 over n, this guy's going to 0. Well, since the limit of the absolute value exists and is equal to 0, not just that it exists, but it has to equal 0, then, or therefore, the limit of our original sequence, negative 1 to the n over n, is also equal to 0. Therefore, converges. Okay? So this is to show you the different properties that we've used. All right. The next theorem that we're going to throw in here is dealing with what happens if we have a composite function, or composite sequence in that matter. So if the limit as n approaches infinity of a sub n is equal to L, and f is continuous at L, so as long as we have those two, we're done with our requirements, then the limit as n approaches infinity of f sub a sub n is equal to f of L. Meaning we look at the inside function, see what's happening with it, or the inside sequence, see that it converges to a particular value. If it does, and the function is continuous at it, then we can say that the limit is equal to the function evaluated at that point. Okay, so to help illustrate that, we're looking at a very basic composite function here of sine of pi over n. So what I'm going to do first is look at the inside sequence as n approaches infinity of pi over n. Well, here this is a nice easy one for us. It's a constant multiple. We're going to get 0 out of it in the end. And here I'm going to be a little bit more detailed about what we're doing. So, and we know that sine is continuous at 0. So by our theorem, we know that the limit as n approaches infinity of sine of pi over n is equal to sine of 0, which is equal to 0, and therefore converges. So this shows that we can still use this on composite functions as well. All right. So here's another fun little problem to deal with, and I like these because you're going to have to get used to seeing factorials pop up, and these situations pop up when we're dealing with series. So, discuss the convergence of the sequence a sub n is equal to n factorial over n to the n. Well, we're going to discuss this. So what's going on? Well, here's some notes that we can make about it. We know as n approaches infinity, both n factorial and n to the n approach infinity as well. So be like, hey, that means we can use L'Hopital's rule, right? If we can find a corresponding sequence or a function. Bad thing is we do not have a corresponding function. And the main reason behind that is the factorial. Factorials are defined for integers only. Nothing else. Well, then, if we can't use L'Hopital's, then what do we have? Well, let's start looking at the sequence values themselves. See if there's something that we can pull from there. All right. So a sub 1 is going to equal 1. A sub 2 is going to equal 1 times 2 over 2 times 2. A sub 3 is going to equal 1 times 2 times 3 over 3 times 3 times 3. Well, this is pretty easy. That means we could write out a sub n, not using this, but looking at it more arbitrary, as 1 times 2 times 3 times so forth all the way up to n, all divided by n times dot 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 times n. Alright? Well, another way I can write a sub n is equal to 1 over n times this value of 2 times 3 times so forth up to n, divided by, well, I've only pulled one of these values out. Alright? They're like, well, why are we going in that direction? Well, let's think about it. I'm going to note one thing. Note the largest value of a sub n is 1. Alright? So, how am I going to use that? Well, if that's the case, think about if the largest value is 1, that means this could be decreasing down, right? So for largest value is 1, that means we're going to be at 1 the whole time, or we're going to be slowly decreasing. Okay? Which means I can do this. I can put this in between 0 and 1 over n. Why am I allowed to do that? Well, 2 times 3 times so forth divided by all these n's, this value times 1 over n is going to be smaller than 1 over n. So that's why a sub n is now in between 0 and 1 over n. Well, let's look at what happens. Well, if I apply my limit as n approaches infinity of 0, I'm going to get 0 out. And the limit as n approaches infinity of 1 over n is also equal to 0. Which means, by the squeeze theorem, you're probably wondering when this was going to come into play. So by the squeeze theorem, the limit of a sub n is also equal to 0. Therefore, converges. And that's it. All right. So here, this is, I am going to post a different video or just a quick example of how to go through this next definition. The proof is very short, but it's something that we can save for another time. So the definition here is the sequence a sub n, sorry, r to the n, is convergent if r is between -1 and 1. Notice here the equality is over on the right hand side. It's a strict inequality on the left hand side. And divergent for all other values of r. And if we look at the limit as n approaches infinity of r to the n, we get a piecewise defined function. It's 0 if we're between -1 and 1, and 1 if r is equal to 1. Okay? And we'll talk about that background with another short video on that part. Okay? Now we're going to talk about some particular properties of sequences and how they can relate to the convergence with that. So we've got to set up some of these definitions right off the bat. So a sequence a sub n is called increasing if a sub n is less than a sub n plus 1. And this is going to be for all n greater than or equal to 1. And a sequence a sub n is called decreasing if a sub n is greater than a sub n plus 1 for all n greater than or equal to 1. Meaning each value next is going to be smaller than the preceding value. Okay, so that's what increasing and decreasing is. We've seen that before with functions. So a sequence is what we call monotonic if it's either increasing or decreasing. Okay, so let's take a second to determine if the sequence 3 over n plus 5 is decreasing, increasing, or monotonic. And how do we prove one of those things? Well, if I want to show that it's, and here we can look at this and say, well, I know the denominator is increasing, so the whole thing should be decreasing. Well, let's check that. That means I want to show that a sub n is greater than a sub n plus 1. Okay, meaning when I plug these values in, I'm going to get 3 over n plus 5 is greater than, you can put a question mark here, 3 over n plus 1. And notice I'm using parentheses here, and I suggest doing the same thing when you're working these out. N plus 1 plus 5. Okay, let's simplify that real quick. So I'm going to get 3 over n plus 5 is greater than 3 over n plus 6. Looking at the denominators, yes, I can clearly see that this is going to be a smaller denominator than that on the right-hand side. However, the smaller the denominator, the larger the fraction, since they have the same numerator. So therefore, this is decreasing, and that's all we can say about it. Okay? All right. And we'll see a little bit more detailed one here in just a second as well. All right. So moving on to the next piece. So this is another property that we're going to be talking about. And we're getting close to the end of this lecture, so we're almost there. So bear with me just a little bit longer. All right. A sequence a sub n is bounded above if there is some number, and we'll call it big M, such that a sub n is less than or equal to this big number. And we're going to say for all n greater than or equal to 1. So what this means is you can look at a sequence and say, okay, we know that it will never cross the value 5. So 5 would be its upper bound. Okay? It is bounded below if there's a number, and we're going to call it little m, such that little m, is less than or equal to a sub n for all n greater than or equal to 1. So that means we can pick a value and it's never going to be smaller than that number. All right. Combining the two, so bounded above and bounded below, if it is bounded both above and below, then A sub n is called a bounded sequence. So it has to be both of them. So it can't be, oh, it's bounded above, so it's a bounded sequence. No, it has to be bounded both above and below in order for it to be called a bounded sequence. So let's look at something that we have seen. Okay, going back to our very first example of when we talked about convergence of a sequence. N over n plus 1. I want to show that it's bounded. So if I'm going to show that it's a bounded sequence, I need to show that, one, there's no value that's going to be greater than it, than this particular value, than the sequence, and there's no value that's going to be smaller than a particular value. Well, we've seen that this thing converges to 1, but it never is equal to 1. So that means I can use 1 as my upper bound. All right. Well, if that's the case, and I know I'm getting closer to 1, that means the smallest it's ever going to be is our first value of 1/2. So therefore, it is bounded above, or bounded below, by, and I'm going to choose 0. So it's never going to equal 0, and it's always going to be above it because it's all positive values. So therefore, this is a bounded sequence. All right, well, we knew that this converged, so does that mean that every bounded sequence converges? Probably, since I asked that question, that means the answer is probably going to be no. So I'm going to give you an example of that. So let's look at the sequence a sub n is equal to -1 to the n. Okay, well, it's going to be bounded between -1 and 1 because we are allowed equality. So it's bounded above by +1, and it's bounded below by -1. Well, it's only going to be +1 and -1. This thing diverges due to oscillation. Okay, so again, make a note to yourself. Not every bounded sequence converges. And this is a good prime example to use. All right, well, what if we have one of those monotonic sequences? Okay, well, I'm going to throw one of those in there. So let's say a sub n is equal to n. Well, this is an increasing sequence. So it's monotonic. Well, think about this. If we looked at the limit as n approaches infinity, this thing is going to blow up to infinity, but it diverges. So here, again, going to put it in red, not every monotonic sequence converges. However, the cool thing is if we combine the two properties together, we get a convergent sequence. So this is our last theorem. This is called the monotonic sequence theorem. It simply states every bounded monotonic sequence converges. And that makes sense, because if we're bounded between two values and it's strictly increasing or decreasing, it's going to approach one of those values. So if we can prove that a sequence is bounded and it's monotonic, we can figure out that the sequence converges. So let's look at the following example. A sub n is equal to 1 minus n over 2 plus n. All right. So what do you think here? Decreasing or increasing? Well, I see I'm making the numerator smaller and I'm making the denominator bigger. And so let's assume that a sub n, and I'm going to put a question mark in here, and we're going to say a sub n plus 1. Well, that's 1 minus n over 2 plus n. And we're going to say that it's decreasing, so this has got to be greater than 1 minus n plus 1 divided by 2 plus n plus 1. All right, simplifying this down just a little bit, we're going to get negative 1, or 1 minus n over 2 plus n is greater than or equal to, putting question marks back on there, negative n over n plus 3. Okay, well that's kind of hard to compare, especially from our previous example. So we're going to cross multiply here. So I'm going to get 1 minus n times n plus 3 is less than negative n times 2 plus n. Once we combine these together, we're going to get negative n squared plus n plus 3 minus 3n is greater than, hopefully, again, question marks there to make sure that we haven't solidified this yet, negative 2n minus n squared. Notice the negative n squareds are going to cancel because they have the same sign on opposite sides. Negative 3n plus n is going to give us negative 2n, so those will combine and give us 0. So in the end, is this a true statement? Is 3 greater than 0? Yes. So this is decreasing. Therefore, we have proven that it's monotonic. Now we need to show that it is a bounded sequence. All right, to show it's bounded, well, if it's decreasing, that means a sub 1 is the largest value of the sequence. And a sub 1 is equal to 0 in this case. All right, so we have this bounded above. By 0. Now we need to show that it's bounded below. All right, so I'm going to take the limit as n approaches infinity of 1 minus n over 2 plus n. Well, this guy, using the same algebraic properties that we have before, this is going to be the limit as n approaches infinity of 1 over n plus 1 divided by 2 over n plus 1. Oh, I left off my minus sign, which gives us a value of negative 1. So this is bounded below by negative 1. Thus, by our theorem, the sequence converges. And we're done with the problem. And that wraps up 11.1. Next, we'll start dealing with, well, what does it mean to be a series, and why in the world have we talked about sequences? And we're going to see how they're interconnected right at the very beginning.